Have you ever found yourself just staring at a massive bridge, wondering how in the world it doesn't just collapse? Well, today we're going to crack that code. We're going to solve an engineering puzzle piece by piece.
You know, the secret isn't some kind of magic, it's pure engineering. And it all boils down to understanding the invisible forces holding everything together.
And to get a handle on those huge structures, engineers actually start small. They tackle fundamental problems, puzzles, really, just like this one. What we're looking at here is a truss, which is just a simple frame of connected bars. If we can figure this little guy out, we can understand the big stuff. So, yeah, let's dive in.
All right, here's our mission. We're basically going to become structural detectives. Our job? Find the exact force being carried by every single bar in this truss, and figure out whether it's being stretched or if it's being squeezed.
And the tool for the job? It's something called the method of joints. And honestly, the strategy is brilliant in its simplicity. Instead of getting overwhelmed by looking at the whole confusing thing at once, we're just going to zoom in and analyze each connection point or joint one by one.
Okay, but hold on. Before we can start zooming in on the joints, we actually have to take a step back and look at the big picture. Our very first move is to figure out the external forces keeping this entire truss in place. Engineers call these the support reactions.
And everything we're about to do is governed by one super simple but really powerful idea: equilibrium. It's a fancy word, but all it means is that everything has to be perfectly balanced, right? If you push down, something has to push up with the exact same force. The whole structure has to be completely still.
So when we apply that simple idea of balance to our truss, boom, we get our first number. Turns out the support over at point C has to be pushing upwards with a force of 2,700 newtons, just to keep the structure from rotating and falling over.
But here's where it gets kind of interesting. To keep everything perfectly balanced, the support at point B doesn't push up. Nope, it actually has to pull down with 1,500 newtons of force. I know, it sounds a little counterintuitive, right? But believe me, without that downward pull, the whole thing would be completely unstable.
All right, now that we've got those external forces locked in, we can finally start our detective work inside the truss. And our first stop is going to be joint B.
So let's zoom right in. We're going to completely ignore everything else for a minute and just focus on this one single point. We already know there's that 1,500 Newton force pulling down here. The big question is, how are the two connected bars, BA and BC, reacting to that pull? To figure this out, engineers draw a super simple little sketch, just like this one. It's called a free body diagram, and you can think of it as our map. All it does is isolate that one joint and show us all the forces acting on that single point. With this little diagram and some basic geometry, we can solve for the unknowns.
And after running the numbers, we've got our first answers. We find out that member BA is handling a whopping 3,900 newtons, and member BC is taking on 3,600. And just like that, we've already solved two key pieces of our puzzle.
Perfect! See how this works? Now that we know the force in member BA, we can use that clue to unlock the next part of the mystery. So let's move on up to joint A. Okay, let's shift our focus now, all the way to the top of the truss. This right here is joint A, and it's where that external load of 1,200 newtons is pushing down. We've got three forces all meeting at this one point: the external load, the force from member AB, which, hey, we just found, and the force from our last unknown member, AC. And guess what? The exact same rule applies here. Everything has to balance. All the forces pushing and pulling on this single joint have to completely cancel each other out. And since we already know the force in member AB, that's the key we need to solve for our final unknown, the force in member AC. And this right here is what makes this method so powerful. By just balancing the forces at joint A, we find the force in our final member, AC, is 4,500 newtons. And with that, our puzzle is complete.
We've now found the magnitude of the force in every single member. So now it's time for the big reveal. Let's put all these pieces together.
But wait, one last crucial detail. Forces can either pull a member apart, we call that tension, or they can squeeze it together, which we call compression. The easiest way to think about it: tension is like a rope in a tug-of-war. Compression is like squeezing a spring. And that distinction is absolutely critical for any engineer.
Okay, and here it is, the final results. We can see member AB is in tension, it's being stretched. Meanwhile, members BC and AC are both in compression, they're being squeezed.
Now we have a complete picture of all the hidden forces at play.
So what's the big takeaway here? It's that the method of joints lets us take a problem that looks really complex on the surface, and by breaking it down into a series of simple, solvable steps, we can systematically find every single one of those invisible forces holding it all together.
So, we've cracked this specific puzzle, but I want to leave you with a final question to chew on. We analyzed the forces with a load pushing down. What do you think would happen if that same 1200 Newton load was pulling up instead? Which forces would flip from being squeezed to being stretched? Think about it.